Hi guys, this is the Teaching Tube, and today we're going to talk about the action potential. If you look at the previous video, Action Potential 1, it talks generally about what the action potential is, how two cells interact via the action potential, how it travels, and in this video we're going to talk about the mechanisms and what happens to create this action potential. So a little bit more of the biology and physiology of the action potential. So first of all, let's start with the diagram of what you're going to see as representing the action potential. You have this weird looking curve, right? So you have what you call here as a resting potential. Resting potential for most cells is around 65 millivolts. Oh, right here. Sorry, the axis here is time, and this on the y-axis you have voltage in millivolts. So the resting potential of most cells is around 65, depending on what kind of neuron it is, can be different. You have this gradual increase, and you have a spike right here once the cell hits this threshold of around negative 40 millivolts, right? And after this threshold is reached, you see a great depolarization. This is what we call this the cell moving from negative 40 or even negative 65 all the way up here. We call it depolarization. So the cell is being depolarized right here, and that's called the rising potential. And then it hits this peak around 30 millivolts, generally in most cells. And then you have what's called a falling potential, and that's called it's being repolarized, right? Because it's getting it's getting pulled away from 0 back to negative 65. So it's getting repolarized, and then you have this dip right here. Interesting. It's lower than the resting potential, and that's what we call hyperpolarized, right? Hyper, more than usual, like hypertension, hyperactive, etc., etc. So this is called hyperpolarized, and also known as the refractory period, and where the cell dips around negative 75 millivolts, and then a short time after, it levels off back to the resting potential. So that's the general shape of the action potential. Now, what goes on to make sure that this happens? How does this happen? And it's all linked to sodium and potassium channels. Previously, we talked about how calcium channels are involved in the action potential, but they're involved in kind of a different aspect of it. So right now, we're just going to talk about the depolarization of the action potential and how this voltage change occurs in the cell. So you start off with the resting potential, and first of all, there's 3 important channels that we are going to talk about today: the leaky potassium channels, the sodium voltage gated channels, and the potassium voltage gated channels. Right? Okay, so these 2 are different. So voltage gated just means that there's a certain voltage that the cell must be at for these channels to open/close. The leaky channels are always open, always on, so always letting things go in and out. So over here what we have is, at resting potential, what we have is that the permeability of potassium channels is greater than the permeability of sodium channels. Now, what exactly does this all mean? So let's take a step back and talk about the Nernst potential and the Goldman equation. So basically, they said the Nernst potential and the Goldman equation talk about how, depending on the permeability of the ions and different things like that, the cell will migrate to the Nernst potential of the ions that it's most permeable to. Okay, so that sounds like a lot of jumbo. Okay, so let's break it down. So what's the Nernst potential? That's basically the difference, right, between how much concentration inside versus how much concentration outside of a certain ion is. So potassium Nernst potential is around negative 70 millivolts. Sodium Nernst potential is around 30 millivolts. Then Goldman came along and he related all of these together and said that the cell's resting potential is actually going to be a combination, so a linear combination of all of these Nernst potentials weighted by how permeable the cell is to that ion. So potassium is most permeable ion in the cell, and that's why you can see that the Nernst potential of potassium is very similar to the resting potential of the cell, which now makes sense why we're over here at the resting potential, right? And so that's kind of goes together and makes sense, right? So in this action potential, you start out with the permeability of potassium channels being greater than the permeabilities of sodium. So, and then you hit this point right here where this is the voltage trigger, right? At this voltage, the sodium voltage gated channels are triggered to be opened, and the potassium voltage gated channels are triggered to be open. However, there's something funny about potassium gated channels. They're slower to open. So right here what happens is you have a huge influx of sodium, and the permeability is a lot greater for sodium. So you have a huge shoot up. But as this goes on, the potassium gated channels that were triggered right here to open, that just took a little longer, open right here. And then you have the permeability of sodium go down, and the potassium is the permeability of potassium is greater now. And actually the sodium gated channels are inactivated. They use this analogy of ball and plug to kind of inactivate the channel, because the channel is technically open, right? Because the voltage is still above the threshold of opening, and right? So, but it's inactive because there's something blocking it. So what you have is a huge permeability, huge increase in permeability to potassium. And then potassium, that's why the cell approaches the Nernst potential of sodium, which is around 30, and then it goes back down. The interesting thing, remember what I said about potassium channels, is that they close, or they're triggered to close right over here, but since they're slow, they close a little bit later. That's why you have this dip. Because the potassium channels are slower, they make this dip right here, which is when the sodium channels are closed, but the potassium channels are open for a little bit longer, and that's why you have that dip right here. And then you're back, once the potassium gated channels close, you're back at this resting potential right here where you get what we